Look up at the night sky on a clear night, far from any city. You can see roughly 5,000 stars with the naked eye. With a telescope, millions. With the Hubble Space Telescope, hundreds of billions of galaxies, each containing hundreds of billions of stars. It is, by any measure, an overwhelming amount of stuff, and it is 5% of what exists. Everything you can see, everything astronomers have ever photographed, every atom in every star, every planet, every gas cloud, every human body, every instrument we have ever built, all of it combined accounts for less than 5% of the total mass energy content of the universe. The other 95% is invisible. It does not emit light. It does not reflect light. It does not interact with our detectors in any way we can directly measure. 27% is dark matter, something with mass and gravity, something that outweighs all visible matter by 5 to 1, something we have never seen directly and do not know the identity of. 68% is dark energy, a property of empty space itself, a repulsive pressure that is actively tearing the universe apart, accelerating the expansion of everything at a rate that has been increasing for 5 billion years. We built GPS satellites using general relativity. We decoded the human genome. We split the atom. We detected gravitational waves from black holes a billion light years away. All of that using the 5%. The 95% has been here the entire time, shaping everything, governing the largest structures in the universe, determining its ultimate fate. And we are only now beginning to understand what it is. This is the story of the invisible masters. To understand dark matter, we need to start in 1968, in an observatory in Arizona, with an astronomer named Vera Rubin. Rubin was not looking for a revolution. She was doing something methodical and unglamorous, measuring how fast stars orbit the center of their galaxies, and whether that speed varies with distance from the center. The expected answer was completely clear. The physics had been understood for 300 years, since Newton. Consider our own solar system. Mercury, the innermost planet, orbits the Sun at 47 kilometers per second, about 29 miles per second. Neptune, the outermost planet, crawls along at just 5 kilometers per second. The farther a planet is from the Sun, the slower it moves. The Sun contains 99.8% of the solar system's mass, and the planets simply respond to its gravity, slowing as they move farther from the source. The same logic should apply to galaxies. Most of a galaxy's visible mass, most of its stars, are concentrated near the galactic center. Stars near the center should move fast. Stars at the outer edge, far from most of the mass, should move slowly. The rotation curve, a graph of orbital speed against distance from center, should peak near the middle and fall off gracefully toward the edge. The curve did not fall. Stars at the outer edges of galaxies were moving at essentially the same speed as stars near the center. Sometimes the outer stars were moving faster. At those speeds, with only the visible mass to provide gravity, the outer stars should be thrown into intergalactic space. The galaxy should fly apart. It should not exist. Rubin thought she had made an error. She checked her measurements. She checked her analysis. She measured another galaxy. Same result. She measured dozens more, then hundreds. Not a single galaxy showed the expected curve. Every galaxy showed the same flat rotation profile, outer stars moving far too fast for the visible mass to hold them. The conclusion was inescapable, and it was enormous. There is mass in these galaxies that we cannot see. Not a small amount, roughly 5 times as much as all the visible mass combined. An invisible halo of matter surrounding every galaxy, extending far beyond the visible stars, providing the gravitational glue that keeps the outer regions in place. Rubin published her results. The reception was skeptical. For years, the physics community resisted the conclusion. But the data did not change. Galaxy after galaxy after galaxy, the rotation curves were flat. The invisible mass was real. We call it dark matter, and it is the dominant form of matter in the universe. Dark matter does not just surround individual galaxies. It forms a cosmic web, a vast scaffolding of invisible filaments along which galaxies cluster, and vast voids where almost nothing exists. The large-scale structure of the universe, the cosmic web of galaxy clusters, filaments, and voids, exists because dark matter formed it first. Gravity collapsed the dark matter into filaments and clumps. And ordinary matter, gas, and eventually stars and galaxies, fell into those gravitational wells. Without dark matter, the universe would be a smooth, nearly featureless place. No large-scale structure, no galaxy clusters, possibly no individual galaxies at all. The universe would be dark, diffuse, and effectively empty of anything interesting. Dark matter is not a curiosity. It is the reason the universe has structure. Rotation curves are compelling, but they are only one line of evidence. What makes dark matter so difficult to dismiss is that completely independent methods, using completely different physics, all converge on the same answer. The second major line of evidence comes from light itself. Einstein's general relativity predicts that mass warps spacetime, and that light, following the curvature of spacetime, bends around massive objects. This is gravitational lensing. The more mass, the more bending. If you know the visible mass of a galaxy cluster, you can calculate exactly how much it should bend the light of more distant galaxies behind it. You can then compare this prediction to what you actually observe. When astronomers made this comparison, they found a consistent discrepancy. The observed lensing was far stronger than the visible mass could produce, in some cases more than twice as strong. The additional lensing is caused by additional mass, dark matter, whose gravitational effect is visible even though the matter itself is not. Gravitational lensing has allowed astronomers to create detailed maps of dark matter distribution in galaxy clusters. These maps reveal enormous halos of invisible mass that dominate the total mass budget of every cluster measured. The most decisive single piece of evidence, however, came from a collision. The bullet cluster is the result of two galaxy clusters passing through each other at about 3,000 kilometers per second, roughly 1% of the speed of light. It is one of the most energetic events in the universe since the Big Bang. During the collision, two things happened that can be measured separately. The hot gas, the dominant form of ordinary visible matter in galaxy clusters, interacted electromagnetically. It slowed down. It piled up in the middle between the two clusters. Astronomers can see it in X-ray observations as a glowing pink region of hot plasma. The dark matter halos, mapped by gravitational lensing, did something completely different. They passed straight through each other. Dark matter interacts only through gravity, or possibly through the weak nuclear force, but not electromagnetism. Two dark matter halos passing through each other simply do not interact in any significant way. They do not slow down, they do not pile up. They pass through like two clouds of smoke drifting through each other. The result is that after the collision, the hot gas, the visible matter, is in a different location from the dark matter. The gas is in the middle. The dark matter halos have continued moving outward, now separated from the gas they used to surround. This is a direct, spatial, geometrically unambiguous demonstration of a substance that has gravitational mass but does not interact electromagnetically. It is a map of dark matter, not inferred from dynamics, not calculated from statistics, but directly traced through the distribution of gravitational lensing. There is no known form of ordinary matter that could produce this behavior. The bullet cluster is the single observation that most directly eliminates the possibility that dark matter is simply ordinary matter we haven't seen yet. So what is it? For decades, physicists tried ordinary explanations. Dim stars too faint to see, black holes too small to detect, cold neutral gas that doesn't emit radiation, compact objects of various kinds. All of these were ruled out. The required quantities are too large. The behavior, passing through itself and through ordinary matter without interacting, is impossible for any known type of ordinary matter. The leading candidates are new types of elementary particles that have never been directly detected. Weakly interacting massive particles, WIMPs, would interact through gravity and the weak nuclear force, but not electromagnetism or the strong force. They would pass through ordinary matter almost entirely unimpeded, accumulating in the gravitational wells of galaxies without colliding or emitting radiation. Axions, extremely light particles originally proposed to solve a different problem in physics, would also be gravitationally clustered, but essentially invisible to electromagnetic detection. Sterile neutrinos, a hypothetical heavier cousin of the known neutrinos, are another candidate. Experiments have been built to detect each of these. Underground laboratories, shielded from cosmic rays by kilometers of rock, contain detectors watching for the rare, faint signal of a dark matter particle colliding with an atomic nucleus. Particle accelerators have searched for dark matter production in high-energy collisions. Space telescopes have looked for the faint radiation that some dark matter candidates might produce when they annihilate each other. After decades of searching, no direct detection. Not a single confirmed dark matter particle. This does not mean dark matter does not exist. Every gravitational measurement confirms it does. What it means is that dark matter interacts even more weakly with ordinary matter than our best theories predicted, or that it is a type of particle we have not yet thought to look for in the right way. The search continues, and the scaffold it provides, the invisible architecture of the universe, continues to hold everything in place. Dark matter was a surprise. What came next was a shock. In the late 1990s, two independent teams of astronomers set out to measure something precise and specific: the rate at which the expansion of the universe was decelerating. Not whether it was decelerating, that was assumed, that was expected. Gravity is attractive. The universe is full of matter. Of course, the expansion from the Big Bang was slowing down. The only open question was how fast. The answer would tell them the ultimate fate of the universe. Slow enough deceleration, and the universe would expand forever, gradually cooling and darkening. Fast enough deceleration, and the expansion might reverse, the universe collapsing back on itself in a big crunch. To measure the deceleration, both teams used Type A supernovae, stellar explosions of a very specific and consistent type. When a white dwarf star accumulates enough mass from a companion to exceed a critical threshold, it explodes in a thermonuclear detonation of remarkable uniformity. The peak luminosity of a Type A supernova is nearly the same everywhere in the universe, like a standard light bulb. Measure how bright it appears, and you know how far away it is. By measuring thousands of Type A supernovae at different distances, different points in the history of the universe, you can trace how the expansion rate has changed over time. Both teams measured their supernovae. Both teams analyzed their data independently. And both teams found the same thing. The distant supernovae, those seen as they were billions of years ago, were dimmer than expected, farther away than a decelerating universe would place them. The universe was not decelerating. It was accelerating. The expansion of space was speeding up. Something was pushing everything apart, not just maintaining the expansion against gravity, but actively increasing the rate of expansion. And it was winning. On the largest scales of the universe, this something was more powerful than the combined gravitational attraction of all the matter in the cosmos. The result was announced in 1998. Both teams confirmed each other's findings. The discovery earned its lead researchers, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. No one had predicted it. No existing theory required it. It was simply there in the data, undeniable. The name given to whatever was causing the acceleration: dark energy. Now, what is it?
The most natural candidate has a history. In 1917, Einstein was working on the cosmological implications of his general relativity equations.
The equations, in their original form, predicted a dynamic universe, either expanding or contracting. At the time, no one knew the universe was expanding, and the prevailing assumption was that the universe was static and eternal. To force a static solution, Einstein added a term to his equations. He called it the cosmological constant, represented by the Greek letter lambda. It represented a constant energy density of empty space itself, a kind of built-in repulsion that would balance the gravitational attraction of matter and hold the universe in equilibrium. When Hubble discovered the expansion of the universe in 1929, Einstein recognized the cosmological constant as unnecessary. He removed it and reportedly called it his greatest blunder. 70 years later, the data demanded it back. The cosmological constant, the energy of empty space, is the simplest explanation for dark energy, and it has a natural grounding in modern physics. Quantum mechanics tells us that empty space is not truly empty. Even in a perfect vacuum, quantum fields are never at rest. They fluctuate constantly. Virtual particle-antiparticle pairs appearing and annihilating on timescales too short to observe directly, but whose collective effect on the energy density of the vacuum is real and measurable. This quantum vacuum energy would have a positive value, an outward pressure, a repulsion. It would behave exactly like the cosmological constant Einstein introduced. Here is the problem. When physicists calculate the expected vacuum energy density from quantum mechanics, adding up the contributions of all quantum fields, the answer is roughly 10 to the power of 120 times larger than the observed dark energy value, 1 followed by 120 zeros. This is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of science. It is not a small correction factor. It is a mismatch so extreme that something must be canceling almost all of the vacuum energy, some unknown mechanism suppressing it by a factor of 10 to the 120. And the residue that remains, the tiny uncancelled fraction, is what we observe driving the acceleration of the universe. Why the suppression is so nearly, but not quite, perfect is called the cosmological constant problem. It is considered one of the deepest unsolved problems in theoretical physics. And the answer may require physics we have not yet discovered. Some physicists propose that dark energy is not a constant at all, but a dynamic field,
something that changes over time as the universe evolves. This is called quintessence. If true, the dark energy of the early universe would be different from the dark energy of today, and we could, in principle, measure this difference by looking at the expansion history across cosmic time. This is exactly what the next generation of astronomical surveys is designed to do. The question of what dark energy actually is, constant or dynamic, vacuum energy or something else entirely, is not just a theoretical puzzle. It is answerable. Given enough data, gathered with enough precision across enough of the universe's history, we can distinguish between the possibilities. This is the most ambitious observational program in the history of astronomy. The Dark Energy Spectroscopic Instrument, DESI, is currently operating at the Kitt Peak National Observatory in Arizona. It is simultaneously measuring the spectra of 40 million galaxies and quasars, spanning 12 billion years of cosmic history. From these spectra, astronomers can determine each object's distance and recession velocity, a precise three-dimensional map of the universe's expansion across time. By tracing how the expansion rate has changed from the early universe to today, DESI can determine whether dark energy has remained constant or whether it has evolved. A constant dark energy value would support the cosmological constant. A changing value would point towards something more complex. In 2024, DESI released its first year of data. The results were striking and unsettling. The data showed a hint that dark energy may not be constant. The best fit model suggested that the dark energy density may have been slightly different in the past than it is today, that something is changing. The result is not yet definitive. The statistical confidence is not high enough to claim a discovery. More data is needed, but the hint is there. If confirmed by future data, from DESI's full 5-year survey, from the European Space Agency's Euclid telescope, from the Nancy Grace Roman Space Telescope, from the Vera Rubin Observatory in Chile, it would be one of the most significant discoveries in the history of cosmology. It would mean that the cosmological constant is not the right description of dark energy. It would demand a more complex theory. And the implications for the ultimate fate of the universe would be profound. Because what dark energy is determines what the universe becomes. To understand the ultimate fate of the universe, we need to think on scales that dwarf our normal experience. The universe is currently 13.8 billion years old. The stars we see tonight will, in most cases, continue burning for billions more years. The Sun has roughly 5 billion years of fuel remaining. The universe as it currently exists is middle-aged at most. But dark energy has been winning against gravity for the last 5 billion years, and it will continue to win. On small scales, gravity holds. Our local group, the Milky Way, the Andromeda Galaxy, and roughly 50 smaller satellite galaxies are gravitationally bound to each other. Dark energy is not strong enough to overcome the local gravity that holds them together. In about 4.5 billion years, the Milky Way and Andromeda will collide and merge into a single giant elliptical galaxy, sometimes called Milkomeda. This collision will not destroy the stars. Galaxies are mostly empty space, but it will reshape both into a new structure. Beyond the local group, the situation is different. Every other galaxy group and cluster is receding from us, and the recession velocity is increasing. At some point, estimated to be roughly 200 billion years from now, most galaxies will have receded beyond our cosmic horizon. Their light will never reach us again. They will simply cease to be observable, not because they have been destroyed, but because the expanding space between us and them means their light can no longer cross the gap.
the night sky will go dark. Not because the stars have died, but because they have become unreachable.
What remains visible, Milkomeda and its immediate gravitational companions, will persist, slowly, quietly, as the universe ages. On timescales of trillions of years, the stars burn out. The most massive, brightest stars last only millions of years before collapsing into neutron stars or black holes. Intermediate stars, like our Sun, last billions of years, then expand into red giants before cooling into white dwarfs. The smallest red dwarf stars, the most numerous type in the galaxy, burn so slowly and efficiently that they will continue fusing hydrogen for 10 to 20 trillion years. Eventually, they too will exhaust their fuel. The last stars will cool and dim. One by one, over trillions of years, the galaxy will go dark. What remains will be a cold collection of stellar remnants, white dwarfs slowly radiating their stored heat into the void, neutron stars spinning down as their rotation energy dissipates, and black holes. The black holes are the last survivors, and they are not immortal. Stephen Hawking showed in 1974 that black holes emit radiation through a quantum mechanical process at their event horizon. This Hawking radiation is fantastically slow. For a black hole the mass of the Sun, the evaporation time is approximately 2 × 10⁻�67 years. For the supermassive black holes at the centers of galaxies, the timescale is even longer, roughly 10⁻⁻100 years. These numbers are so large, they require a different frame of reference. The current age of the universe, 13.8 billion years, written in scientific notation, is about 10⁻⁻10 years. The evaporation time of a large black hole is 10⁻100 years. That is 90 orders of magnitude longer than the current age of the universe. The universe would need to age by a factor of 10⁻90 to reach that point. But eventually, in the framework of the Big Freeze, even the black holes evaporate. The final state is a cold, dark, nearly homogeneous gas of photons, neutrinos, electrons, and positrons at a temperature approaching absolute zero. The universe has reached maximum entropy, the state of least possible order from which no further useful energy can be extracted, no further structure can be built, no further information can be processed. This is the heat death of the universe, the Big Freeze. Time continues, but nothing happens. Nothing can happen. The universe persists in this state of absolute, permanent, frozen equilibrium. Forever is a long time. The Big Freeze lasts forever. The Big Freeze assumes one thing, that dark energy remains constant. That is the simplest assumption. It may be wrong. If dark energy is not a fixed property of the vacuum, if its energy density increases as the universe expands, then the future is not a slow fade to cold equilibrium. It is something far more violent. In the Big Rip scenario, the increasing strength of dark energy overwhelms not just the gravity between galaxy clusters, but eventually every force in nature. The sequence goes like this. As dark energy strengthens, galaxy clusters, currently held together by gravity despite the expansion, begin to feel the increasing outward pressure. The dark energy force pulling them apart eventually exceeds the gravity holding them together. Clusters dissolve. Individual galaxies drift apart. Then, on smaller scales, dark energy begins to overcome the gravity holding individual galaxies together. Stars are stripped from their galaxies, flung into the expanding void. Then solar systems. The dark energy tearing force reaches down to scales where it can overcome the gravity binding planets to stars.
Planets are ejected. Stars stand alone. Then individual planets and stars. Dark energy overwhelms even the gravitational and electromagnetic forces binding matter together internally. Atoms dissociate. Electrons are stripped from nuclei. Nuclei themselves begin to break apart as the strong nuclear force is overcome.
In the final moments, in the last fraction of a second before the end, space-time itself tears. The metric expansion of the universe becomes infinite. Every point becomes infinitely distant from every other point simultaneously. This is the Big Rip. Not a slow death, but a violent, instantaneous, total termination of all structure at every scale. When does this happen? If it happens at all, and that depends entirely on whether dark energy is strengthening. Current preliminary estimates place it roughly 20 to 22 billion years from now. Not an incomprehensible timescale, roughly 1.5 times the current age of the universe. The hints from DESI's 2024 data release are consistent with a dark energy that has changed over time. If that trend is confirmed and extrapolated, the Big Rip becomes a real possibility. Other scenarios have been proposed. If dark energy were somehow to reverse, to become attractive rather than repulsive, the universe could collapse back on itself in a big crunch, the reverse of the Big Bang. This is considered unlikely given current observations, but not impossible if dark energy is truly dynamic and unpredictable. A more exotic possibility is a vacuum decay, a phase transition in the quantum vacuum that could, in principle, occur anywhere at any time, without warning. If the current quantum vacuum is not the lowest possible energy state, if there exists a lower energy state, then a bubble of that lower energy vacuum could spontaneously nucleate anywhere in the universe. The bubble would expand at the speed of light, and inside the bubble, the laws of physics would be different. Everything the bubble encountered would be instantly and irreversibly converted. The process would be completely invisible until the moment it arrives, because it travels at the speed of light, and so does the first signal that it is coming. This is perhaps the most unsettling fate of all, not because it is likely, but because it requires no warning, no gradual approach, no final chapter. Just an ordinary moment, and then something else. The honest scientific position is that we do not know which of these futures awaits the universe, because we do not know what dark energy is. And until we know what it is, we cannot know what it will do. This is not a failure of science. It is the frontier.